I'm a stranger to myself. On these streets I'm someone else. Shadows in the city, like a demon in the dark, come to tear us apart. Me unknown city. Can't tell. 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 Me unknown city. For all my good intentions, there's a shadow in the dark. He comes to me infrequently and breaks your perfect heart. I don't know why I do it, apologize, but it's too late. A single tear and you leave me here and the shadow slips away. Shadows in the city. I'm a stranger to myself. On these streets I'm someone else. Shadows in the city, like a demon in the dark, come to tear us apart. Me unknown city. Can't tell. Me unknown city. Can't tell. Me unknown city. Can't tell. Me unknown
What's up, hackers? Welcome to Attack on Tuesday. I even got the Chiron updated. Tonight, we have a lot to do. We are starting off with our latest ROPEmporium adventure. We're going to do the Fluff challenge tonight. And then after that, really exciting, we're going to explore the just-released CVE 2021-4034. Now, I know that number sounds really low, and it's like, how is it possible that this just got released? I don't really know how the numbering worked or how early. I do know when this was disclosed, actually. And ordinarily, something like this, I would consider this a 0-day, even though something like this I ordinarily wouldn't show this on stream, because the exploit code has been disclosed already. Kind of the cat is out of the bag. So I think it's actually worth going over it and understanding what the vulnerability is, how to detect it, and also how to use it. I believe some orgs get priority to lower numbers. They are reserved. Yes, I imagine that Red Hat gets priority for some of their lower numbers. But yeah, so, and that's a crazy one. As we do it, you'll see it's like an easy button to get root. We'll even see if we have time to root a try hack me box or something with it, just because for a while until this gets patched, this is going to be one of those, you know, get the flag instantly sort of things. But to get started, we're doing some binary exploitation tonight. So let's get the ball rolling there. I've got my tools ready to go. I've got my IPython over here, and I've got Cutter loaded up. I have the Fluff challenge downloaded, and I have the library that has the actual functions for Fluff inside of it, like PwnKit, and I have the binary that uses the library loaded up here. And I've got PwnTool set up in IPython. I've got the binary loaded in as an elf object, just to make it easy. And I've ROPed it as well, so we can look at any ROP gadgets. Can you explain what you're doing in a way that a humble web app hacker can understand? This is a plant question, because I know that Tibbs knows what I'm doing, because he literally wrote the room for buffer overflows. But what I am doing is return-oriented programming. And so basically what we're doing is taking a program, a compiled program, and we're going to learn how it works and exploit the way that it works with a single vulnerability, starting with a single vulnerability in it. And what we'll end up doing is causing the program to move to different points in its code in turn to make it do what we want. Now, this is different than a straight like buffer overflow vulnerability in which we overflow the buffer and we get to inject whatever code into that extra stack space that we want and then execute that code. This is a little bit different than that. It's a little bit more nuanced. And the big reason is the stack in this case is not executable. Right? That's what that NX is all about. So we can't inject code into the stack and run it. That's one limitation. So instead, what we're going to do is we're going to, I'll say this metaphor again. I know some of you have heard it, but I think it's good. What we're going to do is return-oriented programming takes advantage of the fact that functions in the program, even in the assembly, have a return, right? A return at the very end. And if we can find parts of functions, like this address here, that does what we want it to do and then returns, and then we get to control what the next address it does on the stack is, we load those up in order, then all of a sudden we can kind of build a program out of the pieces of assembly that are already in the code waiting for us. A really good analogy for this is, imagine you're taking a video, right, with your playhead, and you're setting, you're entering a series of time codes in the video to make the actors say whatever it is you want them to say, right? So it skips from here to here to here to here to here to make them say whatever sentence you're trying to get them to say. That's basically what return-oriented programming is. And the way that it gets started is you do need to have like a basic overflow vulnerability to kick this off. But then because that stack isn't executable, we do still need to do a little bit of extra work. So let's get started with we'll take it from the top. We'll do the overflow vulnerability, but then we'll see where we go from there. Didn't they do that in Die Hard 4? Isn't that the one with the fire sale? Wasn't that Live Free or Die Hard? I don't know. Maybe. Oh, cool. I guess I know too much about Die Hard. That's actually true. I do know too much about the original Die Hard. In part because the building is in my backyard, practically. Okay, so let's take it from the top. The first thing we're going to do... Isn't it the one where they drove a car into a helicopter? Hey, Ginger. Maybe all I remember is the F-35 in it, and thinking, oh man, that's a cool jet. That did not age well. Especially this week. Die Hard won every Christmas. Correct. It's LA's Christmas movie. It's a great Christmas movie. That's certainly my tradition. We actually had a bad accident with the F-35 this week. Pretty sad. Nobody got killed, but there was a crash on an aircraft carrier on the USS Carl Vinson, and it hospitalized some sailors. He shot down the helicopter with a car. They did that in the Transporter 2, I think, too. They like launched a car off a ramp into a helicopter. Okay, let's do this. So the first thing we're gonna do is we're gonna run the program straight just to see what's up. And, you know, we just give it some input, right? And we get a segmentation fault. Now, we have a couple of ways to figure out what the segmentation fault is. I'm going to show you the, like, canonical way, but then I'm also going to show you where you can look in the assembly to see it. And, of course, I'm using Cutter as my disassembler. Cutter.re. Someone can drop that link in chat if they're so inclined. But here's the way that we usually do it. What is fluff? It's a custom binary? Yeah, it's from ROPEmporium. And if you haven't checked out the ROPEmporium challenges, they are excellent at teaching specifically this thing, at teaching return-oriented programming. So the first thing we're going to do is we're going to create some payload here. To do that, I am going to use the PwnTools command cyclic. Now, I actually have this on the command line as well as in Python. On the command line, it's just like cyclic 100 or whatever else, and it gives me the string. So I can actually do that. I can do cyclic 100 and send that in. But what I like to do is I like to write it to a file, and you'll see why in a second. So in Python, it would be cyclic 100, right? No problems there. And actually, because this is so short, I don't even have to write this to a file. Easy enough. Don't even have to write this to the file. I'll just, you know, do my tmux copy thing. And then I'm going to run it, but I'm going to run it again in debug mode in Ryzen. So I'm going to debug the program so I can look at what's happening. So Ryzen is kind of related to Cutter. In fact, it's the same code underlying it. It's just that Cutter has a nice GUI and Ryzen is the command line equivalent. So I'm going to do Ryzen-D and we're going to do fluff. So -D for debug mode, not flag.txt. All right, loads up. I'm going to run some A commands. A, and by the way, if you want to learn the Ryzen key codes, you just do A and question mark or just question mark, and it teaches you what each kind of thing is. So A question mark tells me that these are analysis codes. Ryzen was spawned from R2. Yes, Radar 2 was a previous branch of development on the same kind of debugger, disassembler. Ryzen's a little bit newer. The developers are a little bit more progressive, basically. And yeah, it's newer, it's shinier, it has some cool stuff in it. I like Ryzen. So we're going to run AAA, basically, because it just runs like max analysis. It does all the stuff that we need, including looking for function names. So if I look for like symbols, you can see I have symbols in here. Was it IF? No. There's libraries. But I've got main, seek to main. I've got the main function in here, right? And I can do PDF to print out in disassembly the function. Now, all it does really is go to pwnme, right? And all of this is stubs because the real function is in the library. I'm probably going over some heads now, and let me back that up. So what we're looking at is in every C program, there's a main, at least in Linux, there's a main function, which is what the program is designed to run when it kicks off. And this program's main looks like this. There's some preamble here handling the registers for the base pointer and the stack pointer. and then it calls another function, in this case, a function called PwnMe. Now, if we look at PwnMe, even when written in nim, yeah, kind of. Although when it's on Windows, it does some interesting stuff with that. There's something called, in nim, there's something called nim main. But that gets called from main. So there's like extra steps, basically. But if we look at the import for PwnMe, you can see that there's this jump to a reloc.pwnme, whatever that is. Well, if we look at it in Cutter, you say there's, okay, jump to PwnMe, and if we look here, there's this thing called a PLT, or procedure linkage table. And what we'll find in the procedure linkage table is the actual, address inside of the shared library that contains the function that we're talking about. So we can use that local address for PwnMe, but just know that its actual location is totally in a different space. It's not going to look like one of these addresses. Okay. All right. So that's that. But we're going to run this thing now. We're just going to run DC to debug and continue. It asks for my input, and I will paste in that big old set of letters. And what's the trick with this sequence is that it is ordered in such a way that any subset of this set only occurs once, basically. And so there's of n length or whatever it is, but basically it only ever occurs once, which means we can use that subset to identify where the break was. So what we're trying to do is there's a buffer, there's this storage space that's supposed to hold our input, and it has to, if our input is bigger than that storage space, if the program hasn't been written correctly, something bad is going to happen. And when I say hasn't been written correctly, if we look at PwnMe in the library, we will see that there's a read function, and essentially our buffer is too small, and we're not checking against it. So we're able to overflow, essentially, the container. All right, so let's run this thing. We get a failure. We get a signal 11, which is a segmentation fault, meaning something went wrong in the code it was trying to run, and that's what we expect, because what we just did, it didn't take 200 bytes. You'll see that in a second. It took at most 100 bytes because we gave it 100. But we don't know for sure how many it took yet. Now, keep in mind that at this point, there's a huge difference between how this works on a 64-bit executable and a 32-bit executable. In a 32-bit executable, we would expect to see a value here that was the hex representation of part of this string. But that's because when you overflow the instruction pointer, and the 32-bit executable doesn't check to see if it's a legit part of the memory space that's been allocated for the program, and it just goes to work and tries to execute that space. 64-bit programs, however, do that check. And so if it finds a bogus instruction pointer, it stops execution. That's why you see the address of 0 here rather than some hex representation of these values. But that doesn't mean we don't have the information that we need. If we do a DR for debug and look at the registers, those really small in 64-bit, the 64-bit slots of memory that the CPU has right on it, right? It's nowhere else. It's not off on the cache. It's not in RAM. Those registers are right there on the die. If we look at that, and that's why they're so fast, if we look at the base pointer register, you can kind of see, if you're used to looking at these, you can kind of see these 61s, which are lowercase a's. Okay, it looks like maybe we got something here. And I have another function called cyclic find. And what cyclic find does is it takes the hex representation of whatever value you detected in your register that broke and tells you what that position was in the sequence, whatever it was. So we're going to give it just the last 4 bytes. We only need the last 4 bytes here. 1, 2, 3, 4. Yep, I can count. All right, so let's do that, and we'll hex, put the 0x in there to encode it. And it tells us that it's 32. So 32 bytes to get to the overflow, right? And then to fill out the rest of the, to fill out the rest of this, to get to the return address, we're going to need another 8 bytes. And consequently, basically, we are looking at an overflow length of 40 in truth. So that's how we learn that. So it's 32 to get to the overflow, another 8 bytes to get over that base pointer hump to get to the instruction pointer and fill up the instruction pointer, and then we're good. So here's the trick to look at this in the assembly. NC Shark, thank you so much for the follow. Here's how we could see that in the assembly. If we go back to the pwnme function, right up at the top in Cutter, it gives us a little bit of a hint. This is semicolons indicate comments in assembly. But even if we didn't have this comment here, we can see the beginning of the function. And you get used to seeing this as you look at more and more assembly. And I'm still learning this too. But we're pushing the current base pointer value onto the stack so it knows where to go back to after it's done. We move, and remember in assembly, in Intel syntax, we go operation, destination, source. So we're moving to the base pointer, we're moving the current stack pointer value. So we're moving that over, and then we subtract from the current stack pointer, 0x20, also known as 32. So that is how much space we have for our buffer. And we can see this right here as well, that our buffer is set up to be 32 bytes. And that's how we know how large our overflow is. If we wanted to just look at the assembly and find that out, that is how we do it without running that test. Now that can get a little bit tricky if you have multiple variables going into a function. This pwnme only has 1, right? RSP was the top of the stack. Yeah, I would think of it. Yeah, that's the best way to think of it, because last in, first out. That's right. The top of the stack. But don't forget that our stack grows from high memory addresses to lower memory addresses. So the addresses fill up in kind of reverse address order, but the stack pointer is at that top. Okay, so we know that we have we have 40 bytes to overflow, and then after that, what happens? Well, unlike a regular buffer overflow, where the next thing we would try to do is like find an address to write to and fill in that spot, right? And set the instruction pointer to that spot and execute that code. Because the stack isn't executable, that's not going to work out for us. So, and in fact, if we look at the symbols tab here, it'll give you some idea of the permissions of the different parts of the executable. And you can see that all the parts that are executable only have read permission on them, right? There's nothing here that has read, write, execute, unfortunately. Hey, Christy. So we have to be a little bit more clever about what we're doing. Luckily, this file, this executable has some stuff for us to use. First of all, if our objective is to print the flag, look at this handy dandy print file function. It's right in here for us. We can look at the implementation in the library here. This is what print file does. We can look at it in the decompiler and see the C-esque version of it. Basically, it takes a single argument, whatever the argument is, which is the file name. And it notes a pointer to the file name, which does matter in this case. And then it opens it up and prints it out. And we can see that in disassembly too. It looks a little bit more convoluted, but definitely we see if we just look at the function calls, which is a good way to kind of separate the wheat from the chaff here. We call to file open, so we're opening a file. And what are we opening? We're opening whatever is this file name. And don't forget that we are using the System 5 calling convention for our functions, which means that when you're calling a function in the assembly, the arguments that you're passing to that function are placed in a specific sequence of registers. In sys5, the first of them is in RDI, okay, or EDI if it's 32-bit, but RDI. So if we look back at our assembly and we see right here on this line, there's a move of to RDI from the accumulator register, whatever that happens to be. And you can see that the accumulator currently has the file name in it, or the pointer to the file name, I should say. So this file name lives somewhere in memory, right? The whole file name may not fit in the 64 bits of the register. So instead, we point to it with a memory address, which definitely fits in that register, right? So we do that, and then we move that value from the accumulator over into RDI. Okay, so that's there in RDI when we call fopen. Because that value is there, file open looks in RDI for its first argument, says, what am I opening? It finds the pointer to that file name, tries to open that file name, and if it works, great, then we move on. If it doesn't work, then we do something else. Same deal with printf. You can see here, printf, we have an RDI function here as well, if it failed to print. Otherwise, we do like a fgets or whatever. So print file works just like that. So if we wanted to, all we would have to do is find a way to load, well, two things. We have to load the file name that we want, in this case, flag.txt. We need to somehow get that value or a pointer to a place in memory that holds that value into the RDI register. Let's back that up a little bit more to see some of that in practice. So let's go back over to our PwnMe and let's... so we know that we have a 40 byte overflow, after which we can do some stuff. Let's start from there. So we're going to start making our payload, and I like to save this as like overflow len equals 40. Okay? And spoiler alert, all the ROPEmporium challenges use the same overflow length because it's not their job to teach you buffer overflows, it's their job to teach you ROP. So they put it in there, but it's perfunctory. But what we're going to do is we're going to make a payload now. And I like to do it now with a list. So payload equals, and then we'll do just 40 bytes of A's, right? Okay. And then what I'll do is with open payload.txt, and we have to open it in write bytes mode as f. We're going to f.write. What are we writing? Well, we can't write the payload right now because it's a list. We can't write that. That doesn't make any sense. But what we can do is do a byte string that's empty and call the join method on it and give it payload. What that will do is it will take all of the elements of the payload and concatenate them together into a single byte string with no separation. If I put a comma in here, they'd be separated by commas. I don't want that. So I'm just kind of smushing them all together into one big old byte string. Why not just do that in the first place? Because this payload is going to change, and I want the ergonomics of being able to change the list of the elements in the payload without having to go through the plus equals, plus equals, plus equals to that payload byte string. Okay, if I quit out of my debugger, I have a payload.txt now. If I cat it out, it might look like nonsense. Oh no, not yet, right? It's just 40 A's. So my terminal's screaming at me. But I'm going to use that payload.txt when I run the program in Ryzen. So Ryzen-R to give it what's called a RZ bin script. And basically we give it the argument stdin standard in equals payload.txt to say, read this in as your standard input, so I don't have to press and I don't have to type that in. Whoops. And then I give it a debug for fluff. So I'm debugging fluff, and I'm doing it with that standard in. Okay. And hey, Gadget Maker. Good to see you. I'm so glad that you got a job that you're enjoying. So now that we have that in, let's go ahead and seek to print file. Nope, we're not going to get there yet. Let's just run it and see what happens. Oh, I did something really stupid, didn't I? I forgot. So we overflowed the buffer, but we didn't put anything else past it. So let's go rewrite our payload. And then we'll just do a byte string of 8 Bs. And then we'll rerun the write. And let's reload the program. Okay, so now we should have... Oh, because we did 40 now, you can see that our base pointer is fully overloaded, right? With A's. The 41 is A's, right? Oh, that song was sampling one of my favorite 80s movies. Right, so if we change that up a little bit, if we had done A times 32 and then a bunch of B's, we would have seen 42. Oh, you get to do testing, teardowns, and articles. Finding a writer's voice has been harder than you thought. Hey, if you ever want to talk about that, let me know. Extra, former English teacher / writer here. But, okay, so now let's do something more fun with this. What we want to do, now that we can control the base pointer, which isn't, like, super helpful in this case, is we want to actually send it someplace. Well, where are we sending it? We want to send it to print file. But to do that, we need to have something valuable in RDI. Right now, there's just garbage in RDI. We don't want that. So I need a way of controlling RDI. Let's see if there is a way to do it. These little bits of assembly that we use to control a program via return, basically like 1 or 2 opcodes and then a return so we can move on to the next thing. These are called gadgets. And I have a lot of ways to look for gadgets in a program. I have one actually loaded in here because I've loaded, you look here, I've loaded my program in as a ROP object because PwnTools has a really cool helper for this. So I'm going to ask for ROP.gadgets here. But that's kind of hard to read. And it sometimes misses stuff. Although there's pop RDI right there. But if I wanted to do it in Cutter, I could. If I go to search, and I search for ROP gadgets, and search in all mapped sections, I go to search, and you can see I get this whole list of little gadgets, right? Here's the opcode, and then the return. Really, really, really handy. The one I want is pop RDI. What I'm saying is I'm going to load some value onto my stack, and pop takes that value off the stack and puts it in that register, in this case RDI. So that's exactly what I want. But I have that, whatever that thing is, has to be an address in memory that is some string. So what I'm going to do is I'm going to look for a value, a string inside this executable that I can use just as a test. And there is one here. This is actually in here by design. There's a string here called non-existent with this address. So we're going to put that right in here. So we're going to say non-existent equals, and then this hex value. Here's the thing, though. I can't use this hex value straight. I have to encode it for little endian 64-bit representation. To do that, I'm going to use the p64 function that comes with PwnTools and kind of wrap this in this value. And just so you can see what that does, let's just call that function. You can see it gives me back a byte string, and you can also maybe see that this whole value is reversed, right? With some changes here, but it's kind of reversed. Yeah, each byte is reversed, right? C4, then 6C, or sorry, C4, then 06, right? Then 40, really, which happens to be the @ sign, and then a bunch of zeros. So remember, for little endian, we flip each byte, or we flip the order of the bytes. So C4 comes first, then 06, then 40, then the rest of the zeros that we need. And because it's 64-bit, we have 8 bytes rather than 4. Okay, so we're going to assign that to a variable, non-existent. Great. So now let's go back to our payload. And we're going to do our overflow length again, times 40, but we saved that value as overflow len. So we'll just do that. And instead of giving it a bunch of B's now, we're going to give it, well, not that yet, because we have one more problem. We have to give it the pop RDI function, or the pop RDI gadget, to say then the next thing on the stack, that's what you're going to put there. So there's my pop RDI. So I'm going to do pop RDI equals, same thing, 64-bit pack that. Now we have what we need. So we'll go to our payload now. Payload times overflow len. And here we'll do pop RDI. Then comes non-existent. And then there's one more thing that we need, of course, which we don't have in here just yet, but I'll save that, which is the address to print file. Now that we've controlled the RDI register and we've loaded it with the non-existent string, I need to call the print file function. We've shown how to look for stuff in Cont'd. Let's show you how to do it in IPython with PwnTools. I have the elf, the program, loaded up. If I do elf.symbols, it gives me a list of all of the symbols, function names and things, and section names inside of the program. So if I do elf.symbols print file, it tells me what that value is, that address is. Now this is in base 10. If I want to see it in base 16, there it is, and that looks about right. So I can say print file equals, and I could have done this with the decimal representation too. It doesn't matter. It's an integer no matter what, but there we go. Now that we've done that, we can just add to our payload print file. Now, there is no file called non-existent in my directory here, so this isn't going to work, but I'm going to get an error that suggests that my ROP is working. So we'll rewrite our payload, we'll quit out of Ryzen, and reload it with our new standard in. Now when we run DC, the first thing I'm going to do, actually, just so we can see it happen, is I'm going to seek to the print file sim.imp, right? Print file. Mishkata Pingvin, thank you so much for the follow. Notice that address 400510 looks very similar to what we just saw before, right? We're going to add a debug, a breakpoint here, so that when we hit print file, the program will stop and we get to examine what's going on. So let's run it. We hit the breakpoint at 400510. Cool. Let's take a look at the registers. What are we expecting to see? We're expecting to see that RDI has the address for non-existent in it. And what was the address for non-existent? Well, over here. It was 4006C4. So let's see what we have in RDI. 4006C4. Looks like we're in good shape. Now, what is actually at that address? We can see that with PX. And just kind of print out the hex dump of the values at that place in our memory. And sure enough, you can see that at that address, we have the following bytes represented in hexadecimal. But over here, we see them represented in ASCII, and it's the string non-existent. So we're actually kind of on our way. Let's go ahead and continue the execution. We'll get the error that no such file exists. Right? Failed to open file, non-existent. But we have the basic theory down of how we're going to print this thing out. The problem is we don't have a flag.txt anywhere in the file. So I can't reference that string. I'm going to have to load it in somehow. So let's take another look at the program and see what I have available to me to help me out with this. And I honestly, at this point, like, again, my mode of speech makes it sound like I have this locked down. I do not. I'm doing this live with you, so you can see the thought process. I understand the theory, but these challenges, they always like to throw curveballs at you. Like xlat b, which we're going to have to look up. But there's this useful function, which is basically showing how print file works. We don't have to use this function. It's mainly just to demonstrate what we just demonstrated here. Because we could have just called useful function rather than do that all manually, but I thought it was worth doing it manually. And then we have these questionable gadgets. So these are the toys that they've given us to play with here. May not be all we need. There may be other gadgets that we need to look for, but these are going to be super helpful. Remember that our primary objective is to be able to write to a place in memory and then be able to reference that place with the RDI register. So the first thing I want to look for is some gadget that allows me to write to a location in memory. And what that looks like in assembly is that my destination, the first argument, is going to have brackets, because those brackets mean I'm not writing into the register, I'm writing into the address referenced by the value in that register. And that's what pointers are all about. If you've ever heard about pointers in C or C++ programming, that's what we're talking about, is these references to locations rather than the actual value itself. So here we are writing to a location in memory that is referenced by RDI. That right away is handy because we know that we can control RDI already. We know that because we just did it. Right? We saw that we have a pop RDI gadget, meaning we can pop something off of the stack, which that's what we overflow and we can add stuff to. We can pop something off of that into the RDI register. So we can control RDI, and now we can say we can give RDI an address to write to, and then what is going to get written there is in this gadget controlled by the AL register, which we'll talk about in a second. Gibbon says, when I see those square brackets, I say pointed to by. Yeah, I do sort of the same thing. Yeah, I usually think the address referenced by. Angel, good night. Get some rest. Thanks for hanging out. So, AL. What is AL? AL is a weirdo. Let's go look at our x64 registers here. This is actually 32-bit registers, but it will do for now. Okay, so see how we have these E's, which means extended here? Okay, imagine that there is another 32 bits on the other side, which is the R registers for each one of those, and that's what makes the RAX, the RBX, the things that we've been seeing in the disassembler already. The 32-bit version of that register, slicing it in half, is the E, AX, BX, CX, etc. The top half of that is AX, right? The top 16 bits is AX. CM Chicano, thank you so much. Welcome. And then the bottom bits, the bottom 16 bits are split up even further into high and low. That's what the H and L are about. So AH and AL. So what are we talking about here? AL is the bottom 8 bits of that 64-bit register. So literally 1/8 of our potential space. And that's all we have control over with that. Which says to me we're probably going to end up doing something annoying, like have to loop through and kind of modify 1 byte at a time, which, whatever, but it is what it is. Maxi Alpha, thank you for the follow. So, following the thinking so far, we can control RDI. We can put an address to write to in RDI. And what are we writing? Well, we're going to write whatever's in AL. We haven't quite figured out how to control that yet, but we'll get there. But before we do that, we have to figure out where we're going to write, because this is what we call write what where. We know what we want to write. We don't know how yet, but where are we going to write it? A little bit ago, we took a look at this symbols tab in Cont'd to look for sections of the executable and what permissions they have set during the run of the program. What I need is a location. It doesn't have to be executable, but it does have to be writable. So I need to have a writable section in here somewhere. Usually BSS or data, really solid for these. Depending on how much you need and what's there. So let's take a look at data. All right, there's like nothing here. Right, it's all zeros. This is really good. All this is really good. BSS is really solid too. That works out fine for me. And to show you what is in fact there, if I look at 60, show in hex dump, 1028, ain't nothing there, right? 6012, not 0, but 8, right? There's nothing there. Got plenty of space. So that's a great location for me to write to. So we'll call that our write address. So we have our where. We know where we're going to write. But how are we going to control AL? How are we going to do that? Let's go back up to our useful functions and our gadgets here and see what we have. Well, we have a couple of weird opcodes, ones that I'm not super familiar with. We have add, okay. There's pop RDX and RCX, and then add RCX 0x. Okay, this might be just something we have to account for. And we have the STOSB AL. We should probably test to make sure this does what we think it does, because STOSB, we haven't actually seen that before either. This isn't like the greatest documentation, but I actually really like it for this. So it says, let me zoom that in a little bit, stores a byte, word, or double word from the AL, AX or EAX register, respectively, into the destination operand, which we saw. The destination operand is a memory location, the address of which is read from either the ES EDI or the EDI registers, which that's all exactly what we just discovered, right? So it is kind of just a write. It's like a move. I don't really know what the difference is. Other than you have a little bit more control maybe over the size. I don't know. But there it is, and it does what we need it to. To prove that point, here's what we're going to do. We're going to get our... Let's put that address into a variable. Hey, duct tape! We're doing some binary exploitation. So what was that? That was... this is why I have a transparent terminal. STOSB... RDI, and this is just kind of the way that I've figured out how to do my convention for stuff. Adder is for addresses. AL equals P64. x86-64, you know it. Yep, we're doing a ROPEmporium challenge. Okay, so we have that. And we have our write address. And yeah, when I have one monitor I can use, the transparency is super helpful, right? I can have two things up at the same time. So here's what our payload is going to start looking like. Overflow length is good, but instead of the pop RDI and the non-existent, we can do a couple of other things. Instead, we want to set up the STOSB. We just want to test just that thing to see what happens. And in order for that to work, I'm going to set a breakpoint at that location when we go to debug it. So we're going to write that out as our payload. Reload up Ryzen. And we know that this is the address we want to breakpoint at. So we're going to copy that address and put a breakpoint there. And we're going to run DC. What should happen is that we're going to just hit that breakpoint right away. Which we did. Good. In order to test how this thing works, what I need to do, because remember, this thing is writing, well, it'll work this way. I didn't control RDI. So what is an RDI right now? In RDI is this 7F E958, this garbage here. I probably should have made it something useful. And what is AL right now? Remember that AL is the lower 8 bytes of the AX register. So B, does that fit in the lower 8 bytes? It does. Or 8 bits, I should say. Does the value, remember, 8 bits, can I represent the value 12, 10, 11, sorry. 11. In 8 bits? Definitely. So that fits in the AL register. And so what should happen is... unfortunately, though, I can't write to this address because it's garbage. So instead, I'm going to kill this process and try that again. We're going to change our payload up. And we're going to pop RDI. And we'll do our write address, which we already had. And then we'll do this. I need a comma. There we go. So we're popping the value onto RDI, which is our write address, which is where we want to write. And then we can use this STOSB opcode. Okay. One more time. And let's go get that address for breakpoint. Okay, we hit the breakpoint. Let's take a look at our registers again. Okay, this time RDI looks sane. That's our right address, which we looked at before. And AX is B. Now, think about where we are. We are... We're right here. We're right on this instruction. Then after this next instruction, this will have happened. And that's exactly what I want to have happen. So instead of running DC to continue, I'm going to run DS to step, just to move one instruction down. Now, this cursor hasn't changed, but if I do a register inspection, you'll see that my instruction pointer is now at A rather than at 9. So it's moved down by 2 bytes, right? The ret and then whatever's next. So now... Or this is just the ret, because the instruction was 2 bytes long. So now I'm going to take a look at this write address to see what's in there. If this thing has worked the way I hope, there should be a B in there. Or an 11, if you want to think about it that way. So where's my... There it is. Isn't it 8? Whoops. No, 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 no. It did not work. Let's move one more. I think I broke it. Let's try that one more time. Interesting. It incremented that by a byte. Overflow, pop RDI, the right address. Bit operator, thank you so much for the follow. STOSB increments. Oh. See, I was thinking of it as a write. No, I mean... There's a byte or a double from the AL into the destination operand. Destination operand is a memory location. No, at the assembly code level, 2 forms of the instruction allowed. So, 4th paragraph. Ah, thank you. After the byte, word, or double word is transferred, EDI registers incremented or decremented automatically. Thank you, Captain Gibbon. Okay, so that part worked, although, interestingly... Ah, there it is. It didn't break. So it did actually write to the correct location. Thank you for clarifying that. So STOSB increments. That's interesting. That is a difference than a move, or from a move. And there's our B. Just waiting there. It's not really a B. It's an 11, right? But that value is present in that location, which means we have a way of writing to writable memory. Cool. Now we just got to figure out how we're going to get flag.txt in there. Well, let's take a look at some of these other gadgets that we have. We have xlat B, which I assume is meant to be pronounced translate B. And since we're on this page, there's xlat. There we go. So what does translate do? Locates a byte entry in a table in memory using the contents of the AL register. Interesting. As a table index, then copies the contents of the table entry back into the AL register. That is really interesting because that means that we do have a way to control what is in the AL register. It's just that it's going to be kind of weird. The index in the AL register is treated as an unsigned integer. So basically, if it's like a 0, right, then we look. Let's look at that call. .b. So whatever's in AL is the reference. Gets the base address of the table in memory from either EBX or the BX registers. The DS segment B. Okay. So whatever is in the BX register is going to be basically the thing it's reading from in turn. And that the table in memory, so that's the base address. So whatever we give it is the base address, right? And then the AL register, whatever that has in it, it starts at 0. Well, it starts at 0B, but you know, if it were at 0, it would start at either the PX registers. The assembly code level, 2 forms of this instruction are allowed. Okay. And can we control BX? Kind of. That's where these come in, I think. So we have STOSB, we have XLAT, and we have BExtract or BExt, which is not here. Did I read that wrong? BEXTR. Is it E? No. Let's just look for BEXTR. Felix Claudia has it. Okay. Extracts contiguous bits from the first source operand using an index value. And so it's very similar to what we were looking at before. Extracts contiguous bits from the first source operand, right? Using an index value and length specified in the second source operand, meaning argument 3. Bit starting bit is supposed to start a bit of a bit extraction. Interesting. So if we look at how this is being used, so going into BX is what we have in our CX and DX, and using an index value and length value specified in the source operand. Extracts contiguous bits. Bits, notice, not bytes, from the first source operand using an index value. So we have some pieces to put together here, basically. It can be helpful to diagram this out. Think about what we need to do here. You might think that Vim is not great for diagramming, and you're not wrong, but it's how I do it. So what we eventually want to do is we want to be able to print file with RDI. Right, so we need to be able to write to RDI. And how can we write to RDI? We can write to RDI, or we can write to actually, that's not that. It's like that. So how do we write to RDI? That's with pop RDI. Cool. How do we control RDI? We control RDI with stosb byte RDI AL. Okay. So that is how we control that. Let's put a little directional thing there. Okay, how do we control but what is it that we want in there? Actually, we're missing a step. Right, because we want the right address, which is and then that's how we get that in there. But the problem is AL, right? So how do we get AL going? And the way that we're going to get AL going is, it seems like xlat b, right? Because if we translate, because what translate does is it reads from AL, but it reads the results back into AL. So somehow we're going to have to do that. And notice that, so xlat b, and I'm going to just put in parentheses that it's reading from EBX, right? So how do I control EBX? Well, we have this, the B extract RBX, RCX, RDX. Okay. Time to go sideways. I apologize if I'm, like, infuriating anybody with my diagramming method. I find it easier to do this than do a mind map, like in a mind mapping program. I don't know why, I just always have. So how do we control EBX? It was... Oh, cool, I'm glad you're digging it. That was right, B extract, right? Let me turn on insert mode here. BXter, RBX, what was it CD? RCX, RDX. Okay, cool. So what this should do is allow us to write to BX. And then RCX and RDX, what do those do in this case? Right, contiguous bits using index value and length value special for the second source operand, third operand. Well, we know that we have a gadget here that does... Oh, no. We're not controlling BX there. We're controlling C and D. And we know that we have pop RDX and pop RCX. So we have a way to control both of those. So we have a gadget to do that. Cool. But then there's a little bit of a complication, right? Because if we look at the gadget, which starts here, it pops RDX off the stack. It pops RCX off the stack. And then it adds 3EF2 to whatever RCX was. So we're going to have to just, like, account for that in whatever we do. We're going to have to, like, pre-subtract that value so that when it adds it back in, it's what we want it to be, if that makes sense. And if it doesn't, folks, please do ask questions. I know that I'm kind of monologuing a lot here, but thinking it through. But if I'm not being clear about something or something is still fuzzy for you, please ask. Okay, so we can pop that onto the stack. And we can get RDX onto the stack. Then we're good, right? So I guess we need to just figure out what those things are. Oh, what is it that we're getting, basically? I think we, in turn, have to find some values. So what goes in here to C and D? Let's read this again. This is the tricky one. Here's source operand. Second operand, right? Index value and length value specified in the second source operand. Oh, wild. An index value and the length value is in the second. So bit 7 to 0, meaning the first 8 bits of the second source operand, specifies the starting bit position of bit extraction, a start value exceeding the operand size. Okay, bits 15 to 8, the second, specifies the maximum number of bits. Interesting. God, what a pain. God, what a pain. This is, Good night, Christy. Thanks for hanging out. Good Lord. So RBX is here. And then what's this? Hold on. Second source. From the first source. So it extracts from the first source. So we got to extract from the first source. So the first source is RCX. And what is RCX going to be? Well, we know that it's coming from pop RCX, right? We know that. But what is RCX actually? Meaning, what is the source going to be? It has to be some value. First time to see a live reaction to the channel. What a pain. I mean, it is. It's meant to be. But, I mean, it's fun. I'm having fun with it. I'm not angry or anything. It's some string, basically. And we're going to extract how much? Well, you wrote this challenge. Gasp. Well, first of all, let me say thank you, because I have learned so much about ROP and all the others, you guys. Yeah, I mean, I put that together, but thank you so much. I have learned so much about binary exploitation because of these challenges. I'm really grateful for the work that you've done. Thank you so much, Captain Given. Okay. So RDX. Oh, thank you. Oh no. I'm learning, but I'm glad that folks are getting stuff out of it. It's a real pleasure. I'll tell you this, you know, as a fairly new hacker, right? And as a prior web developer, doing low-level stuff was always kind of a goal for me. And resources like ROPEmporium have been invaluable in getting me to a place like this where I can speak with some level of understanding about what's going on the stack and going on in the registers. It's because of challenges like this. So absolutely fantastic work. Okay, so RDX needs to be this crazy situation. So the first byte, I should say, right? The first 8 bits is the starting position of the extraction. So that's like 0, right? And then the second is the maximum number of bits that we're going to extract. So, okay, so we're pulling from here, and we're pulling this index and this much, putting in here. Now, I don't know how lucky we're going to get, you know? There's no flag in here or anything, right? Let's look for, what strings do we have in Fluff? I guess there's FL, you know? There's an F and an L in here. There's an F and an L in here. So whatever this is. Yeah, I don't think that's actually a thing. Okay, so we've got 2 characters there. Got A's. Places. God, this is going to be weird. Okay. Well, let's try this with just an F. You know what I mean? Because these are, I don't think these are readable, right? Yeah, no. There's another way to look for this stuff. I think. Which is, I have the elf, right? And I have dot. Elf.search. Yes, good. Elf.search. Search the elf's virtual address space for the specified string. I have a couple other ways I could do this too. I could do this in Ryzen. Elf.search F. Generator object. Oh, give me the byte string. Dope. All right, here's what we're going to do. Flag adders equals. This is a fun one. We're going to do elf.search. Oh my god, why can't I type? C. And then we're going to just do the next invocation here to get the first result. For C in flag.txt. Let's see what we got. You know what I should have done? I should have hex encoded that, right? Let's see what that looks like. 403C4. I mean, it's not wrong, right? Hey, Czar. I've managed to go this whole time without making a stupid mistake, and you haven't even been here. Okay. Were you proud? That looks right. If we were to go to that address, just trying to write an exploit. Hey, bud, guess what? We're doing that next. We actually have the exploit. It's wild. It's so crazy. Yeah, I want to knock this off so we can get to that. Let's look at that disassembly. If we put that address in, right? It doesn't look like anything here. But yeah, that looks right. Because 1, 2, yeah, 2, 1, 2, 3, 4, F. And then actually, presumably 3C5. Oh, there was an L way before that, so it found that first. Very funny. But that's fine. That's so cool. Okay, so we have the flag addresses. Fluff page is updated. Like, as of right now. Beautiful. J-Raw solved this challenge the same way. That's amazing. So in terms of bits, we're talking about 8, right? So it's like for every one of these strings, we're going to pull some string. So that's the address we're going to load into RCX. Except we have to subtract 3EF2 each time, which is idiotic, but we're going to do it. And then RDX is going to be, if we look at this, the B extract, right? It says that bits 7 to 0, first 8 of the second source operand specifies the starting bit position of the bit extraction, which would be, in this case, 0, right? And then the start value, and then the 15.8 of the second source operand specifies the maximum number of bits. Oh, okay. So actually, we're saying 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, and then zeros, 0 1s, 0 2s, 4s, 8s. Or God, I hate that. I know that there's a way to do that. I just don't feel like doing it right now. But we have to. But so far, this is intended as best as I can remember. Insane that I'm something like on the money here. Okay, so let's take a look at our payload and also potentially let's start writing out our exploit.py because I don't want to have to do this kind of again and again. So let's see, we have write address equals that. We're just going to get all our stuff down. Okay. Pop RDI is that. I used a way easier gadget for this challenge. I'll tell the address of it when tag ourselves. Okay. What else do we need? We need the... Oh, we actually didn't even do the pop RCX RDX stuff, but let's go get it. Pop RDX RCX add. Hold on a second. Let me save this as a... Save that out. And then open that up in a second tab so we can have it available. I wanted my see-through pane to see addresses and stuff. Pop RDX, RCX, add, crap, equals, if anyone was going to find it, it was going to be Czar. And We have pop RDI. We have that. We have the right address. Oh, we need the flag. Little fun Vim magic for everybody today too. Okay. Unnecessary vimming, but handy. That's so cool. Okay, so let's see. Oh, we have our overflow length as well, right? And filler equals overflow len. That's right, Vim equals love. As a matter of fact, for our most elite subscribers, we have a Vim emote. A while ago, I did a whole thing on teaching how to use Vim for maximum power. It's, you know what? It's nice to be back in Vim. I've been in VS Code for so much of the Rust and Nim stuff that I've been doing. It feels good. I feel like a heathen for never bothering a little bit. So one of the things I've found is that even as a by day security analyst, Vim is a superpower. I can parse through CSVs or log files so much faster because of using Vim. It is utterly invaluable. Don't know what I'd do without it. I'd probably fart around in VS Code, but I don't want to have to. I'm so much faster in Vim. You feel like you should move from Vim to VS Code? You know what? I think both have value, and I use both of them. They're good at different things. Like, I would not have wanted to write all the Rust I've been writing recently in Vim. Would not have been a great... Yeah, VS Code is great until you haven't got a GUI. Exactly. Or if you want to do cool stuff like this. Like, I don't know. I'm not a tiling window manager guy, but I do love tiling my terminals. Tmux plus Vim is a powerful, powerful 1-2 punch. Okay, so for each one of these things, what are we doing? Love doing Ruby on Vim. Ooh, boy, Ruby. I haven't thought about Ruby in a minute. So, payload equals, we're going to start building the payload here. That's 0? All right, whatever. Okay, so our payload is going to be... I thought this would be easier for everyone to see. So we're going to start with it being our overflow length. Or, sorry, our filler, I should say. And then it's going to be pop RDI. And our write address. No, wrong. Wrong. Go back to our diagram. First thing we need to do is is this a buffer overflow kind of exploit? It starts as a buffer overflow, but the real nature of it is that it's a ROP. It's return-oriented programming. So what we're doing is we're looking for little bits of assembly that we can use to compile, piece together the instructions we want to do to create our exploit in the program already, rather than injecting a bunch of code, because we can't. So I guess the first thing that we have to do is the pop RCX, right? Because we have to control this. Right, because it's pop RCX RDX, right? No, it goes pop RDX, pop RCX, and then add. Right, so it's actually pop RDX RCX add crap. And then, you know what? There's no reason to do that here. Okay. For A in flag adders, what we're going to do is payload plus equals. And it's plus equals because we're concatenating the list. So, or we're adding to the list. So, like, if we do 1, 2, plus 3, sorry. I can't, if I do, like, x equals 1, 2, I do x plus equals 3. Oh, come on. I guess I'm just going to do an append. Why was I thinking that I could do a plus there? Why was I thinking that? Doesn't matter. Anyway. Well, yeah, I can do that, but I don't think that's what I don't know what I was thinking of. Whatever. Doesn't matter. Payload.append. Our pop RDX, RCX, and then add. And so what do we want in RDX? Let's go back to our diagram. RDX is going to be whatever our value is, which I'm pretty sure is 8. But I'll also say that's the part I'm least confident about. Yeah, that's the part I'm least confident about because I don't feel like I'm totally grokking that part of that opcode sequence. Okay, but then once we do that, then payload dot end. What goes in RCX is some string, the flag address, right? But it has to be, oh, you know what? These shouldn't be P64'd. Okay, I'm not gonna lie, I'm pretty happy with myself that I got that in one go. These shouldn't be P64'd because we need to subtract that asinine value to prepare it for this. Nope. What was that? 3EF2. And once we do that, I feel like I'm missing something. Next comes the translate, right? It's a byte of the BX. Because now that we've controlled that, moves it into AL. Right. Oh, you know what? Write address shouldn't be P64 either. Not yet. But here we do which loads whatever is in BX. Wait. Uh-oh. Am I outthinking myself? Where's our B extract? RBX, RCX, RDX. Yeah. So now we're going to do B extract, right? Here. Okay. I'm annoyed that my autocomplete is off. So I'm just going to go ahead and solve that in another window at the same time. Dim plugged. You complete me. Fine. Okay. I have to compile my autocomplete plugin, annoyingly. I'll be the first to admit that this challenge is an enormous path. Well, you know what? I'm deeply honored that my testimony to such is now on the page. So xlat b, right, moves a single byte back into AL. So for every one of those, so at this point, AL theoretically should have the byte that we want. So now we do pop RDI. You know what? Now I know why I was thinking plus equals. It was a list. Let me clean this up. Much better. Much cleaner. That's what I was trying to do before. xlat b. Then we're ready to do pop RDI. Or no. Not pop RDI. Where's my STOSB? STOSB. Yes. And we actually do want pop RDI, don't we? Because the way this is going to work is, yeah, we have to put the address in, and then we write the byte to it. So pop RDI. Then we're going to do, oh, this is fun. I need the count of how many flag addresses I've done. So to fix this, I'm going to do AI in enumerate flag addresses. Because what that's going to do is give me what enumerate does, if we do it in IPython here just to see it, enumerate if I give it a list of 1, 2, 3. Or sorry, let me give it string so it's clearer. B. God. Okay, this is one thing that I like really don't like about Python 3 is that it has this weird intermediary generator for a bunch of stuff that I just want. It is probably smart that it has that, but just give me the list. It has that for filters and maps and stuff too. Okay, so you can see that it produces a tuple of the index and the value for each of the elements in the list. And that's super handy for stuff like this. So I have the value, but I also have the index, except it should be reversed. It should be IA if I want I to be the index. Okay, so I've got the index, I've got the address, and pop RDI. Why did I want that? Because I want the address, or I want the P64 version of the right address plus I, because we're adding 1 byte at a time, right? Every time we do this thing. So we pop RDX, RCX. RDX gets the value of 8. RCX gets the address that we're pulling from minus the junk. We extract into BX what we have in CX, which is the address, and we extract that many bits because it's bit extract, right? Then we translate, which puts 8, which puts the contents of BX into AL, and I only have 8 bits that I can work with at a time. From there, I can pop RDI. I pop the right address plus I, and then, so this is the part now that I get to pull from AL into the right address. That's what we have Stosby for. Yeah. Now, I feel like I'm forgetting something important here. Bill Stosby. Bill Stosby, Employee of the Month. Super duper dupe. Thank you so much for the follow. Okay, here's what's sticking in my craw. The original value in AL/AX, right? That B. What are you doing? I am doing binary exploitation, return-oriented programming. And I promise you that you've never met less of a bro in your life. That original value in AX, is that going to mess with us at all? It is, right? Because the first time through this, buffer overflow is where it starts, but we can't do a traditional buffer overflow. We're doing return-oriented programming. We're doing ROPEmporium. Let me send you the link. Does that original... No, you know what? It doesn't, because translate B is going to write into... Right? Translate B is going to write... Oh, crap. No, it does. Locates by using constants of AL register as a table index. Urgh. So I have to account for that somehow. But it's only on the first one, right? And where is that going? It's going into... whatever's in BX, right? Into BX. So the first run through this, AX is going to be set to B, and I need to handle that somehow. And that bites me when? That bites me... Does that bite me at Stowsby? Yes. Oh, it bites me way before that, actually. Contents the AL registers table index. Yeah. Copies the contents. The AL register is treated as an unsigned integer. The xlat and xlat b instructions get the base address of the table in memory. Can I just... There isn't... I don't have like a way to zero out AX, do I? That would be just the greatest. No. Doesn't look like it. I don't think so. And that would be a weird one, too. Pop RAX is, like, That would be very weird, right? Because the whole thing with AX is the accumulator. It ends up being the result of an operation in the code. That's like the purpose of the register. Okay, let me just think this through for a second. So the problem is that the read index is going to be off by 10 for the first one. Meaning that in B extract, or is it translate? Yeah, in translate, in translate, the first time we do that, copies the contents that the index in the AL register is treated as an so the first time, like 10 later, it's going to be off. So oh, I think I got it. If I equals 0, accounting for the RAX, else string adder equals A. And here we'll just replace this with string adder. Okay, at which point we're done with the byte stuff, or like the individual character stuff. So then we're ready to do payload plus equals pop RDI, write adder, and print file. Okay, before I read Czar's wall of text, is it Czar telling me that there are gadgets that can't be found by ROP-Gadget or easily? Remember, sometimes gadgets produce instructions that don't make any sense but are still valid because they're disassembled from the middle of other instructions. For example, if you have a legit instruction in the program, move RAX. Yeah. I remember when you told me that before. But unless I miss my mark here, which totally possible, this could just be complete nonsense. I think this solves the problem, because I'm accounting for that particular location, that particular value in the first one. Oh. Well, we'll see. Okay. And what I think I'm going to do is I'm going to just have this write out the payload rather than run it in here so that we can do debugging with it. Notice that my autocomplete started working. Very funny. See, this is my yeah, my IntelliSense, my hints are working now in Vim, which is it's a really nice tool. It can get in the way sometimes. It's called You Complete Me. Print file is not defined. Okay, so it's not. Let's put that up here. I promise we're going to get to the CVE today. I promise we're going to do it. Item 66. Expected a byte slice. Did I forget to P64 something? I did. Forgot to P64 it here. Hey there, Guar. Good to see you, buddy. Great. Okay. Let's close that up. Let's load up Ryzen. AAA. And what I'd like to do is set up a couple of breakpoints. In our weird gadgets here. And this one in particular, really curious about what this is going to do. And Stowsby, of course. And did I hit the extract? No. Okay. So the first one that we hit was 62A. Let me open up the exploit down here. Um, 62A was the pop RDX, which if we look at our payload, is exactly right. That's the first thing that we should have hit. Okay, cool. So let's continue. The next thing we should hit is B extract at 633. Great. Let's take a look at what we have here. So let's look at our CX. Our DX has the value 8 in it. Our CX has the string address minus whatever this value is. So let's step 1. Because we're at 33. Oh, actually, let's see if that string value matches. 3B9. Well, except it actually has to be, if we did that right, it should be the love of God. All right, so that value looks correct. At least the math is right. Let's go ahead and continue. All right, we hit 633 again. 628 was X late. Excellent P. Let's continue. Ooh. Something bad happened. Yeah, I don't think it totally happened, though. Let's take a look at our write address. I think something must have gone wrong here. Okay, we haven't written anything. And where did we get the error? Uh, 400628. Translate B. That's not it. Oh, look at that. We got B in our address. So it's like, were we off by a byte somewhere? Pop RDX, pop RCX. We didn't get to the... No, we did get to the B extract. And we went back to translate B. And okay, so what happened here? Locates a byte entry and table memories the contents. Okay, so AX was still at B, which we knew. And BX was 0. That wasn't supposed to happen. Let's run that one more time. And just put that single breakpoint in there. Okay, 628. Let's see what we have. AX is still B. That hasn't changed, so we're still on our first run. Our DX is 8. The RCX is on that first address. And we're ready to translate B. So what should happen is use the contents of the AL register as a table index and the BX. So first of all, oh crap. It's supposed to be reading from EBX, but EBX is empty. Why is that true? Because I transposed the B extract and the translates. I just did the same thing, didn't I? No, I didn't. Oh, no, that's right. That's right. But it's not, B extract is not doing the thing. Extract continues for the first operand. Yeah. Oh, I think I know what the problem might be. I could be totally off my rocker. Hey, Joe. Everyone, the mayor is in the building. I think I know what the problem is. I could be totally wrong, but this was the part that I was like most on the fence about, was this 8 bits for how much we're supposed to pull. And I think I'm getting literally flipped around with Indianness. If it isn't, if it's not at the beginning, it would be at the end, which means I have to pull the whole dang register, which would mean it's all zeros anyway, except for that, wherever that is, 64, because it's a 64-bit register. Again, could be totally wrong. But let's try that again. Okay. 64 minus 8. Why 64 minus 8? Yeah, so my thinking, Czar, is that the register is 64 bits long, and the 8 that I need is like on one end of it, and I was pulling way on the other end. So instead, I need to pull the whole thing. You know what I mean? And then that'll capture the value and put it in the right spot. And we're going to do another, because the xlet b is what we're trying to test here. Okay. So we've hit the translate b. The b extract, if we've done this right, something should be an RBX. Crap. Nothing is an RBX yet. CX, DX, DC. CX, oh, so, yeah, because look, CX is here, DX, oh, but you know what? We saw 8 in there before, but then I need, why isn't xlat B happening? This is the part that's failing. Hey, Pat the Cat Patter. I am not ready for a red versus blue challenge tonight, but rain check, okay? We will do it. There's another thing that I want to do tonight before we end, which is we're going to take a look at that new Linux 0 day, because it's bananas. But I want to get this done. I'm braked at 628, which is the translate. Thank you, Czar. Thank you, Czar. It hasn't run yet. Let's try that. DS. Oh, that broke. But there's still nothing in RBX. For some fun. You know, Pat, I'm happy to do a one-off with you. Those games take way too freaking long. And I'm like, they're cool once in a while, even with backdoors and breaches. Like, I don't know. The truth is that we're doing so much real stuff on here. I like the idea of having some sort of fun competition. Let's think it through a little bit more to see what else we can come up with. All right, so that didn't work at all. We just hit, so we went back to 628, but we got a segmentation fault. And so that didn't help us at all. We don't know that it was right or wrong, but So this is where the problem is, right here. The string address thing. And I'm seg faulting, I think, because it can't read the right string address. Now, the first string that we pulled... the address ends up correctly in RCX, yes. And the number of bits actually showed up correctly, too. So that part's fine. The problem is... somewhere else. Okay, let's not do this and see what happens. I know that this is going to be wrong in other ways, but let's see what happens when we don't account for the 0xb. Okay, we're breaking on the translate again. Okay, so let's see. 8 bits in RDX, 3C4 in RCX. Now, what is there? What is at that address? Okay, there's an F, actually, which is cool. But the problem... And actually, let me see that again. So, and what is 10 bytes later? Okay, there's a dash. But that's fine. So we know that there's a dash there that we can kind of test. Okay. So, then... Wow, we... segfault immediately. We segfault immediately on the translate B. So something is going wrong here. We cannot... Something about this we're not understanding. Set AL locates a byte entry in a table in memory, using the contents of the AL register as a table index. Okay. It's definitely in AL. The rubber ducky, that's what I've been doing the whole time. All of you are just rubber duckies lined up behind the camera. And I mean that in the best possible way. Using the contents of the AL register as a table index, then copies the contents of the table entry back into the AL register. So, okay. We died. Did something happen to AX? Nope. The index in the AL register is treated as an unsigned integer. Fine. Xlat B instructions get the base address. Yeah, Tibbs, we're getting close to the end here. Get the base address of the table in memory from either... Get the base address. the assembly code level. No. So the index here, in this case, is B. And then BX. EBX should fit this address, right? Or... Oh, wait. Okay, so this is the problem, right? Because I'm saying it's reading from EBX, but EBX doesn't exist yet. And how does it start to exist? Bextract should have done it, right? That's why xlat b is failing, because 0 is no good. Bextract isn't doing the thing. So we got to figure out what's going on with bextract. Yeah, extract contiguous bits from the source operand using an index value and the length value specified in the second source, which we've done. And here we go. So bit 7 to 0, the second specifies the starting bit position of bit extraction, which is 0. And the start value exceeding the operand size will not extract any bits. The start value exceeding the operand size. Right. Bit 15 to 8 of the second source operand specifies the maximum number of bits. No to this song. There we go. Only bit positions up to operand size minus one of the first source operand are extracted. Only bit positions up to operand size minus 1. I'm in 64-bit duct tape. The extracted bits are written to the destination register starting from the least. And the operand is is 64 bits. So it's got to be okay. So I also need the other registers. I don't know what you're talking about, man. But this does have to be 64. Look at the page again. The gadget that I have, duct tape, is bextract to RBX. I know. Bextract to RBX from RCX and RDX, right? And I have a gadget that pops onto RDX and RCX. Which I have. I have those. All right, let's rewrite this with the 64-bit. The extracted bits are written to the destination register starting from the least significant bit. All higher ordered bits in the destination operand are zeroed. The destination register is cleared if no bits are extracted. Huh. All right, let's break on the bextract. Now let's see what we have. Okay. 64 bits in RDX. Which, right, is Bits 7 to 0 seconds. Starting bit position. Oh, uh-oh. Maybe that's the problem. Maybe that's the problem. The issue here. If you look at the first two lines under operation header, start length source 2 15 to 8. Yeah, I think I'm seeing that too. That the 64 is not really the right value. Yeah, exactly. Exactly. The start value, and we were seeing that before. So basically, why can I not do binary values in Python? Why am I messing with that? 0b. That's right, of course. So the first 8 bits freaking starting position. So it's 0. Yep. And then the next 8 are the maximum number. So no, 1s, 2s, 4s, 8s, 16, 32, 64. Great. Wait, wouldn't that still be 64? Wouldn't that still be? Yeah, I don't, like, that would still be that, right? It would still be that. Unless it's flipped. Okay, in which case I was an English major. I'm not built for this. 1, 2, 4, 8, 16, 32, 64. It's Little Endian. Now, interesting. So 4,000. All right, let's take a look at that B extract again. Okay. Okay. We didn't crash. And BX is 3C4. Unfortunately, that's not going to work out. So I have to go back and fix the... Okay, let's just see. So let's look at our write address and see how we're doing here. I think we're close, friends. Okay. So I think that's we're writing to the right address. But we got messed up because I think the thing I had with the accounting for the 0xb at first was actually what we needed. GIFRM, considered a hot box on HTTP, but if you know how to run crackback with LDAP domain dump and Bloodhound Python, it's a relatively easy box to pwn. Totally unrelated. So it definitely got like mutated, but that's because we need to. Previous comment was recommending Xbox logbot search. I still don't. I mean, thanks for the recommendation. I still struggle to see how it's related to what we're doing here with binary exploitation. I do appreciate the recommendation, though. Okay, let me re-add that thing I had before where it was like string adder, like if I equals 0, string adder equals a minus 0xb. Else. Because we're plainly writing to the thing, right? Nope. I'm using none of those things, GIFRM. This is Ryzen, not R2. Well, we got the F. But some of these other values seem a bit mutated. Oh, wait a minute. Hold on. This is an index, right? Is it A minus? Having never used PwnDebug, I can't talk about the advantages over it. This is just what I've gotten comfortable with. Oh, right. Oh, right. Okay. Okay. So here's the deal. Okay. What ends up in AL is an index, right? And after we pull from it, it gets written back to it. So essentially, after we write to AL or whatever the first time, that's the new index, right? Whatever that value is. So we have to subtract that again. Okay, so have to be like... and then there, that way I don't have to... Basically, I'm gonna say if I is not equal to 0, right? Then we say we're just gonna modify RAX. RAX equals because it's whatever ends up from the I minus 1, because it's 1 after. Okay, so then if we do, we have to do 2 subtractions. Okay, I feel good about this one. What? Oh. It was A? Yeah. Wait, crap. If I is not equal to 0, so I minus 1. I'm using the PwnTools library. It's just Vim, but yes. What is my issue here? P64A minus RAX. I don't understand what argument out of range means here. These are all integers. These are all integers. Line 36, P64A. So that's the problem. I can't P64 that for some reason. Oh, wait. I'm being an idiot. Yeah, it's way too big. Because it's not the address that gets written back to AX, it's the character. Right? So what I actually need... Okay, yeah. Okay. What I actually need is to save this string. That we're trying to write. And it's not the flag adders, it's the flag string that we have to handle. And unfortunately, I have to convert this to an int. In order to make that work, I think. So that ran. I forgot to put in a breakpoint. We are getting to it. We're so close. Tanho28, thank you so much for the follow. Where's that xlat B? Bites are happening. Wait, no, that's not what I want. I want the right address. Hello? Dot? T? Hey, what the... Why did I segfault? I was so close. What? Why? Why did I segfault there? X got written. Check the whole chain made it onto the stack. Why am I at address D? It's a good question. I know I didn't run out of room. I definitely didn't run out of room. The place I was writing was... Go to symbols. Here. FLAG dot TXT. Plenty of space. All right, let's run it again. FLAG dot T. Too far. So X gets written, and then my payload might be too long. Well, I don't know a way of making it any shorter. FLAG dot T. Okay. So 74 is in here in AX. Right? There's T, which we have to subtract out. And then the next address. Oh, look at that. Why is 1D2 doubled up? Oh, wait, no, that's right. That's right, because RCX. So I'm now at 400629. I'm now at A3. Whoa. How'd I get all the way down there? Worst case, you could try to run the exploit 2 times and get half the flag each time, thus reducing the ROP code. Link, I don't see how that's possible. I need the full file name. I need flag.txt in there. Symlink to the rescue. I mean, okay, look, we plainly have the concept down. We're writing to the thing. Yeah. Yeah, we hit a ret and we ended up at 6A3 somehow. Can you verify the chain continues from about the right last T? Well, it segfaults after it writes the X. It writes the X and then dies. So the last thing that happens is it writes the X. It's failing somewhere in the last iteration after the xlat b. Is this a size issue or the letter X issue? I don't know. But because I promised the 0 day, and I feel like we did the concept here, I'll work this a little bit. I think we're dang close. I think we're gonna call it for right now and move over to this 0 day. So yes, Czar, show us the gadget that you used. As I get this up and running. So here's the write-up from Qualys about this insane CVE. Put this in the link. So CVE 2021 4034. And what's crazy about this is look how low the number is, right? And it's from 2021, but it's just now getting disclosed. 4005E8. Oh, cute. What's there? What does that end up looking like? I actually don't know how to do that. Do I do like an obj dump starting there or something? Anyway. New disassembly, maybe? Yeah, what does that end up as? But let's take a look at this 0 day. So this has to do with a program called PKExec, which if you've ever looked for SUID based exploits on a box, you have found something like this, right? Find perm 4000 dev null. You found PKExec in this list somewhere, even though it's taking a million years for this to load. But it's in the list all the time, and you'll see it and just like, okay, whatever, go past it. But it turns out that it's been vulnerable to something. Hey, CyberGummy, it's been vulnerable since its creation in May 2009. And it's pretty wild. So it's a memory corruption, but let's take a look at what happens, the way that it says it. So in the beginning, yes, we're talking about PwnKit. So the beginning of the main function processes the command line arguments in order. But the way it works, Captain Gibbon, thank you so much for the subs. If the number of command line arguments argc, the count is 0, and then the argv list. So in any C program, right, the main function takes two arguments. Argc, the count of arguments on the command line, and argv, the array of arguments on the command line. And, or really it's the string of the arguments. But the point is that if the argument list is empty, then it skips over it and it starts reading stuff into wrong positions as it reads values in. So it says the pointer path is read out of bounds from argv1 C string. Thanks, duct tape, because I don't actually write any C. I've learned Rust, so I didn't have to. But what exactly is read and written from these out of bounds? To answer this, this has to do with how execve works. The kernel copies our argument and environment strings to pointers to the end of the new program. For example, splitting it up like so. The TLDR here is that what we're able to do if we use execve specifically to pass values to PKExec that are empty, it starts reading in environment variables that we get to set as essentially argv, right? So what's interesting there, right? If our path environment exists and if the directory name exists, contains an executable name value, then a pointer to the string name value is written out of bounds. In other words, this out of bounds write allows us to reintroduce an unsecure environment variable like LD preload into PKExec's environment. So we get to introduce environment variables, but here's where it gets crazy. There's a very specific environment variable. XDTech, thank you so much for the follow. There's a very specific environment variable, if we come down a little bit, that makes this crazy. And by the way, this write-up was out before their own, Qualys' own proof of concept, but it was so clear that people had exploit code in minutes, basically, because it's that easy. So inside of this function for converting text formats is this use of this environment variable gconv path. And it turns out that if you load something in a gconv path, then specific functions inside of how the conversion work are going to look for functions in a shared library that you're providing and execute them. And so this exploit that I found, this was the first one I saw, it was from a guy named Blasty, takes advantage of that. So this exploit is a one-hitter, and what it does is it first compiles the shared object for you. It writes it out. Oh, you know Blasty? Yeah, you Dutchman. So dangerous with your boats. it writes out the shared object and compiles it for you, then runs the exploit. So this is what the shared object looks like. This is the library that you're creating. You created this gconv init function, which is what is expected in the library for the code in pkexec to call. So it sets UID, the effective UID, the GID, it sets this all to root for you. And then it builds the environment variables, right? Or it sets that these would be the environment variables, set the path, right? And then it calls binsh. And then exit when you're done. Then it GCCs it, it sets it up as a shared object, all good. Now here's the actual exploit. We create environment variables, nothing, then this path equals gconv. And then LC messages. This is important in order for gconv to get called, I believe. And a couple of others, basically, that are getting read in. Then it is checking for the presence of gconv path. And then looks for all this stuff. Does the file open, writes to certain paths, and then it just calls at the very end then with all this set up. And look, under 100 lines, it calls pkexec with the argv and envp. Now, this affects all modern systems. I'll just put it in the binx. Thank you, all modern Linux systems. This has worked on every single machine I've tried it on. Obviously, patches need to be coming in. Now, here's the problem. There are no patches out yet for this, so it's kind of scary. But if we go back to the write-up, they do make an important point here. The exploitation technique leaves traces in the logs. Yeah, exactly. The value for the shell variable was not found in etsy shells file, or the value for environment variable contains suspicious content. However, please note that this vulnerability is also exploitable without leaving any traces in the logs. But this is left as an exercise for the interested reader. All Hack the Box are now Sam the admin or PwnKit. Well, Sam the admin only works against domain controllers, so no. But between that, Print Nightmare, and PwnKit, there are a few barn burners out there that are still quite viable. So let's see, sudo system, journal CTL. All right, didn't find that. Would it be in D message? No. Red Hat, Ubuntu WSL, Kali. It is, I think it's everything. Everything that uses PolicyKit or PolKit. I don't think it is. Duct Tape, I don't think it's going to work on OS X because it doesn't use PolKit. Did I link the GitHub? I didn't. I pulled this into my own GitHub gist for myself. You can go find Blasty's stuff out there. Go look for CVE 2021-4034. But I want to be careful here because this is a dangerous exploit that we don't yet have a really good defense against. So just be aware of that, right? And I want to help build detections against this because it's nasty. Yeah, I don't think it is in there. Yeah, the post here says that you can do it without leaving a trace in the logs. I don't know if that's what we've done here. Maybe. Maybe that's what these... Maybe it does. Maybe that's what these extra garbage variables are about. All right. But I think we're going to call it a night. It's been a long, long stream. Thanks for hanging out, everybody. Sorry we didn't get the full flag, but we did get some good stuff going on in binary exploitation. We'll see if we can figure out what the problem was next time. And we'll be back tomorrow doing some programming. So hang out then if you're interested. Until then, be good to yourselves, be good to each other, and we will see you next time.